So I will be talking about the ACORN project, so on automating concrete construction, on the holistic approach that we have to produce low carbon structures, so concrete shells for building slabs. My role in the project is a postdoc researcher focusing on the fabrication side of things. Sorry. So I will start with an introduction, giving some context. So you might be aware that the construction industry presents nearly 50% of the UK's carbon emissions. But something that's maybe less, figure that's less voiced is that slabs actually represent the majority of the embodied energy in a building, ranging from like 48 to 78%. Of course, varies of the type of construction, of the height of the building. But that still has a major impact compared to columns or beams, etc. And if we consider that in the energy that we need to produce a building, the energy that a building will use, the operational energy for heating and cooling during its lifespan is now really a minor part of the total amount, and embodied energy is the part we need to tackle. So if we talk about concrete, so a big part of it comes from cement, the production of cement, which is responsible globally for 7% of global greenhouse gas emissions. However, this is not the only thing that impacts the environmental footprint of concrete slabs or concrete structures. Usually, concrete slabs are highly reinforced with around 40% of a carbon footprint. In volume, it might be much less than concrete, but in terms of environmental impact, it's still significant. And another thing is that the formwork that we use to actually shape this fluid material that is concrete, the labor of the time that is needed to here in the case of this image on the right, to shape this timber plate can be up to 50% of the cost of in-place structural concrete production. So these are these three aspects that you need to think about when you're assessing the environmental impact of a concrete structure or concrete slab. I think one of the main thing is that, so when we design a slab or even a beam, usually we have this prismatic shape that are easy to build, made of timber formwork. So, and actually this shape favor a bending behavior, as you can see on the slide. So you need this set of blue compressive forces and red tensile forces. So you need a thick slab to give it some structural depth, and you need to actually reinforce the slab to carry the tensile forces. But the interesting thing is that these prismatic shapes are simple to build. However, if we want to actually reduce the amount of material and energy that we use, then our philosophy is to turn to shell systems. And the key change between these two systems, from plates to shells, is this lateral or horizontal arrows in green that allow to give some thrust to the system and allow to, with a curved structure, to carry loads mainly in compression, which allows the structure to be thinner and less reinforced. So that relates to two of the first three topics I mentioned. So less carbon, less cement, less reinforcement. However, due to its curvature, this is harder to build. And this is not a new concept. So vaulted structures for roofs and ceilings and slabs have been done as a first way to build slabs. Here I just stole a couple of pictures from Pinterest where you can see this fancy looking roofs that are maybe a bit peculiar, but they actually show that they can be integrated in actual buildings, and curved structures are not just meant for airports or train stations or stadiums. sorry. In terms of research backgrounds, there's been some interest in these curved slabs for building building systems. So I will just mention the Ripman floor system developed by the Bloxer group at ETH Zurich, or more closer to us, so the doctoral research that has been done by Will Hawkins at the University of Cambridge and Bath with John Orr and Paul Shepard. So you can see there's some interest in this, and our goal will be to push it further. And so to do so, our approach is actually to have this, let's say, large-scale project with multiple partners or universities from Bath, Cambridge, and Dundee to work on automating concrete construction. This project is actually part of a Construction 2025 a scheme from UKI, and out of the 4 goals of this scheme, we actually focus on the first 3, which is lowering costs, emissions, and improving delivery. So to achieve this, we have this holistic team from, so again, Bath, Cambridge, and Dundee. Well, we actually want to have this so holistic approach end-to-end, so including computational design, advanced modeling and fabrication, structural testing, and actually assessing the environmental impact of a process and its potential, or how to actually have also positive impact on the construction industry and change the way people think as to use just the amount of material or energy that is needed. We have multiple project partners that are there to advise us, guide us, and also challenge us, so that what we are doing is meaningful. And CSIC is actually part of it. And we have also a couple of project affiliates that are more interested in it and are just following up our research and keen to know more and collaborate. So our approach, or the main assumption for our approach, is for automation, is to do off-site production. So here you can see a picture of a Langer manufacturing hall. And to do so, we won't be doing it at this scale in Cambridge, but in case you haven't been to the lab in the last couple of days, you can see the 2 new residents on the strong floor. So we got funded by the NRFIS, 2 robotic arms that are almost 3-meter reach, and that will allow us to do some advanced manufacturing and automating fabrication. I will talk a bit about the design of our shells, our concrete shells. First, starting with the shape. For now, we've explored a couple of standard shapes that you can see on the screen, where we try to understand so how this system works, analyzing are there many working compression, which is what we want, or is there some tension, how much? So there's some exploration in that sense, and also some parametric design studies on regarding the span. So what span makes sense as an application for this system, what thickness would be needed, or how much height would these slabs take, and how to integrate it into a building. But the next steps, the key steps, will be how to do some more proper form finding, shape optimization of this. And the key thing, as I said, is to have this holistic approach where design has specific objectives, and we will take into account the construction or fabrication process that we will develop, that will inform as a feedback loop design, to have this construction informed approach. And this is how we will actually be able to reduce the environmental impact of our designs by assessing the sustainability of the entire process. So not just the amount of material that we use at the design stage, but to make sure that this is also easy to produce and to construct without resorting to a massive amount of extra formwork and labor at later stages. Now, so it was just a quick glance at the shape, but I'll talk about the segmentation of it. So in the instant, like for beam, if we assume here we can see a concrete, or let's say a slab supported on its four corners. And if we assume that we want to have this span of 8 meter by 8 meter, which is regular for offices or maybe a bit higher also for housing, then we have actually first a transportation constraint. So we can have long elements up to 12 meters, but we have this constraint in terms of width, so which can be bounded by 5 meters. So we would actually need to segment or split this shell into multiple pieces. And actually, in our case, we have also some production constraints that we'll detail later. So on the formwork of the mold that we will have in our lab, so to produce 2x2 or 4x1 elements. So how do we actually segment this based on these constraints? So we also want to have a smart, we cannot just have strips, we want to take into account the flow of forces in the slab. So here, heuristically, the main force flow would connect the support. So that's why we have these diagonals and straight arrows along the edges. And one proposition that we've been investigating is this segmentation, where you can see the interfaces or the key interfaces between the segments is aligned with the flow of forces. That way for structural reasons. And each element fits within this kind of bounding box of 2x2 and 4x1. And to complete the system, then we'll have some post-tensioning to make sure that the interfaces between the segments is not just compression only one, but you have some post-tensioning to improve its structural behavior. And one also interestingly, so it's not just about the structural behavior, but also having a simple way to assemble it. So here on site, you can see that this segmentation will allow this sequential assembly, starting on the left with one diagonal that could be erected as such. Then the second diagonal would come to complete the system, and so on until the entire shell is assembled. At the moment, we've done this small scale prototype. So we've really printed the different segments using a transparent PLA. You can see that the colored elements are actually trombones, so it gives you a sense of a scale. So that's 50 by 50 elements, where we could actually try our assembly sequence ID, and we actually, so it was produced by Diana, one of our colleagues, and she had her kid load testing it by standing on it, and did not fail. So now from design to fabrication, and first with a formwork that we will developing. So we have a couple of main functions that we wanted to achieve. So we want it to be reusable. We want it to be reconfigurable so that we can shape different geometries for the shell. And for automation, we want to also actuate it so we can be integrated in this digital workflow. And we were really inspired by the adaptive molds developed by, for instance, Adapa company in Denmark. And there have been many research projects on such molds for composites or facade concrete elements. But I will just mention what Foster and Arab did for the Kuwait airport, where they actually use it to produce the bracing concrete panels that fit within this steel frame. However, what we want to do is to produce structural concrete elements, not just bracing panels. So this will be our contribution, how to integrate all of these new features. We actually commission the department, so 4 modules, so 1x1 modules. So that's why I mentioned previously on the segmentation constraints of 2x2 or 1x4, because then we'll be able to actually, that's what we'll be able to do with these modules, to reconfigure them to actually get this such a pin bed mold or formwork, and to produce our elements. This is still in fabrication, but I can show you what the prototype that we did in February. on a different type of mold. So here we don't have these vertical pins as before. We have, you can see here the mold with these flexible rods made of GFRP that you can actually bend and put into shape to get a curved structure. Then the second step was to add different features. So by features, I mean here some air reinforcement strategy, some spacers and some threads in order to connect it afterwards. Then we sprayed concrete on it, and then we could actually just demold it from the frame and the membrane, and get our small here, 1 by 1 piece of shell. So I mentioned a couple of things, so concrete and reinforcement. So our strategy for concrete is to do some spraying. Why? Because that will allow us to have this compaction of the concrete on the curved surface. And that's actually some process that's easy to automate, or it's already been automated. It is really popular in the tunneling industry. And you can see from this image in the previous prototype, or the first prototype that we did, that this was manually done. But the next step now is automation. Since we have got the robots, we'll be able to try the path for spraying that we will computationally generate. So how do we actually find the path in order to get this shell with a thickness that we want to control, and a quality of concrete that should be as good as classic processes. So on a curved surface, it's hard to actually control locally the thickness because of its curvature. And I won't go too much into the details, but the work we've done recently was how to compute some kind of path based on specific curves that the surface has that are called orthogeodesic. And this path actually has an interesting property that, as you can see from the circles that represent the spray influence, that you actually, even if it's the surface is curved, you get this nice control of this nice spread of or distribution of the circles, and that should allow us to actually get a good quality process. Another thing that comes from it is the spray orientations, because that's as it's known in the industry, as we could try. It's important to be orthogonal to the surface. It's also important to be at this 1 meter or 1.5 meter range. So these are all computation work that we'll be able to test and calibrate soon. So now the reinforcement. Previous work that's been done by John Horn is filament reinforcement. You can see here on this beam that the filament reinforcement was wound with to get this optimal layout of shear reinforcement in black. You can see the process on the top right, where you have this mats that can rotate, and this station with the roving of filament that can translate, and from this you can produce a layout that you fine-tune, or the production of this optimized layout. In our case, we won't be so from beams to shells. We're actually prototyping this. So first on a plate, but you can imagine how it will extend if you just have a curved surface. And what we'll be working on is how to actually through this set of vertical pins, how can we get a robot to grab a filament and wind reinforcement around it. The reinforcement that will be winding are optimized, or they will use a minimum amount of material. How do we do this? So from the set of elements that we had before, we take into account all the different combinatorial set of lines that can connect them, along which you can actually add your filament. Then we can perform we can model the equilibrium of the shell with a strut and tie model and optimize it so that we find this a network of compressive struts in blue that are forces taken by the concrete, and tensile ties in red where we actually need to put the reinforcement or the filament. And since each tensile tie will require a different amount of forces, we can, and since we know the cross section of our filament, we know how many passes we need per element, and from this we can actually compute a continuous filament path that the robot can follow to wind the reinforcement along these pin elements on which we can anchor our filament. Yeah, so how do we actually evaluate that what we do makes sense? We start with performance. By performance, I mean two things. There's structural performance. So there will be some, sorry? So there will be some material testing to actually evaluate not just the layout of the materials, but actually the process in itself with the spraying, the winding, etc. So there will be some structural testing at the scale of a shell. But another thing will be monitoring the structural behavior by embedding sensors. That's something we'll be working on with CSIC. We're not at that stage at the moment, but that's one of the interest in the project. And so by performance, I also mean this performance and the sustainability. It's not just about, as you can see in this life cycle assessment circle, so it's not just about extracting at the beginning the minimum amount of concrete or cement or manufacturing a minimum amount of reinforcement. It's also about the construction aspect of things that comes later, and to now do actually fabricate them. So we'll have this life cycle analysis of the entire process to guide us and check whether the decisions that we are making are in the right directions or not. And regarding, so another part is the impact on the industry. So as I said, we have multiple project partners that will help us for it. And the first thing is to actually consider complete design briefs. In this presentation, I've shown, let's say, simple shapes or square shape, but actually you have to take into account many things. So you can see a plan of a building in West Cambridge, and you can see that you have with different column layout or wall layouts, you have various spans. You locally have some cantilevers, but then you also have to integrate different shafts or openings for conduits. You also have then fire safety reasons, vibrations, acoustics. Building also has to take lateral loads, not just horizontal, not just vertical loads. And these are all things that maybe we won't solve them all during this project, but we at least have this map of constraints or of aspects to think about and to consider. Another thing is so we will have this, we will be working on this holistic workflow, so from design to production. But this thing, but it will be used and it will make sense only if it's ready for people from practice, from engineering or architecture. And to do so, we are actually interested in what Bureau Apple, who's a collaborator in the project, has been developing for years on which is a library on interoperability between the different platforms and softwares. And so our aim is to actually develop our work within their framework in order to make sure there's a smoother or easier use of our work by people from practice. But the main thing will be the demonstrator that we'll be building at the end of the projects on the BRE Innovation Park in Watford. I can give you the guidelines that we have at the moment. So we won't be doing a proper house or building. So we'll be building a structure, but design to integrate all the various aspects of that a regular structure should, so opposed to a just self-standing pavilion. What we probably go for is a one-level structure, 2 bays, around 8 meter spans, but they will be covering different spaces, so not just square or rectangular spaces, but there will be some skewed, they will have some skewed footprints. And so just to conclude and to actually stress on the philosophy of the project, so we will manage to produce this low carbon concrete shells for buildings if we have this holistic approach. So design, construction should have a dialogue in between and be informing each other. And the performance will not be on the material, but just the sustainability of it, which has to include the entire design to construction process. Thank you.